Here we go, everyone. Welcome to lesson 14.3. Welcome to a sick Mr. Wagner trying to do his best to get through this lesson. So I will do the best I can to be audible, to be understandable, despite this cold that I'm battling, or sore throat, or whatever this nasty thing is that's lasted for a few days here. But we're looking at all this stuff here, especially today, is focusing on Hamilton Pass and Hamilton Circuit. So we talked about Euler Pass and Euler circuits already, and there's another dude, his name's Hamilton, and he did some pretty groundbreaking work in graph theory as well. And so some of the things we have in graph theory are named after him, and specifically for this lesson, Hamilton Pass and Hamilton Circuits. So let's say we're going to get started right with an example right now. Example 1, suppose the following table, what table you ask? Oh, we'll get to that in a moment, shows the cheapest one-way airfare between the given cities. And so let's draw a table. Let's check this out. And you just need 5 lines, 5 rows for this one, so it only has to be that big. But also going to have 5 columns. And then I'll use yellow for these ones. These can just be the blue lines on your paper. Just going to use the yellow here to keep things nice and straight. Alright, that's looking pretty nice. And we're going to find the distances between, or not the distances, but the airfares between Los Angeles here, Albuquerque in New Mexico, Phoenix, and San Francisco. Okay, so this is our graph. We've got 4 vertices, and we're going to be connecting those with edges, each city to each other city, and we're going to find the airfare between each one. So let's put up here Los Angeles, Phoenix, San Francisco, and Albuquerque. So Albuquerque. And then over here, same cities. I'm going to put, after Los Angeles, I'm going to put an L. That will stand for Los Angeles. After Phoenix, I'm going to put a P. San Francisco will be an S. And Albuquerque, there we go, will be an A. And so there's no flights between Los Angeles and Los Angeles. You're already there. Same thing with Phoenix, San Francisco, and Albuquerque. So I'm going to put little slashes through those. I just need to fill in the rest of these here. And so when I purchase flights myself, I usually use this website here. It's called Kayak, kayak.com. So I'm going to be typing in, I've got LAX, that's Los Angeles. I'm going to be typing in Phoenix, San Francisco, and Albuquerque. And so let's start with Phoenix. And which one do I want? I think I want this one. So we'll go with that. We're not going to add nearby airports. And I'm going to say any day of the week. And so we're just going to pick a particular week here. I will pause the video and bring up what we get for our flights. Okay, so I've changed it to one-way LAX to Phoenix. I'm going to go on the Wednesday and plus or minus 3 days. That will give me all days of the week. And I actually want to go to the 27th. It looks like this might be, well, no, it's disappeared. But it looked like that first week might be a spring break type thing, so a little more expensive. But let's find flights. Let's see what happens here. And so, really, wow, is this for real? We got a $69 flight. Is that cheap to go from LAX to Phoenix? I guess it's not that far, but that's what we're going to be putting in then. This is a one-way flight from, I guess, oh yeah, the other one was round trip. Alright, so LAX to Phoenix, we have $69 for the cheapest flight. So let's go back to here, and let's put that into our table. So 69 will be here, and we're going to assume that the flight back, or a flight from Phoenix to LA, will be the same as from LA to Phoenix. And so both of those will fill in with a 69. And let's go back to the excuse me, to this here, and we'll change this to, we want to go now LA to San Francisco. And so I'm going to be pausing as I go here. You don't need to see me type everything in, but let's do LA to San Francisco now. So it looks like that was $84. And maybe a little bit longer, not by much. This is a map from Google Maps, so this should be drawn to scale very accurately, I would say. From LA to San Francisco, 84. And now finally LA to Albuquerque. Let's check that out. Right, so it looks like that's $125 for LA to Albuquerque, and we'll assume the same for Albuquerque to LA. Okay, so now we still have to figure out Phoenix to San Francisco and Albuquerque, and then finally San Francisco to Albuquerque. So let's type those things in next. So Phoenix to San Francisco looks like got a flight for $119. So we'll put that here and here, and then next Phoenix to Albuquerque, and that flight $84. So we got that showing up twice. That's okay. Phoenix to Albuquerque, surprising though, that is exactly the same. And San Francisco to Albuquerque, last one. And as I thought it might be, it looks like the most expensive one. Makes sense because it's the longest trip. $150 for San Francisco to Albuquerque. So we have all our information now, and we can draw a graph. So we're going to use this table to create a graph, and the vertices will be labeled with L, P, S, and A for the cities you see here. And I'm going to simplify this a little bit. So we could draw a graph just like this. This would be perfectly drawn to scale, but I'm going to bring Albuquerque up a little bit, San Francisco down a little bit, so that the vertices are a little closer. And so this will look like this, this, and this. So honestly, you could put these vertices anywhere, but I think it's a good idea to at least keep them relatively in the same general areas that they're in before. So let's draw our graph. Remember, these don't have to be perfectly straight lines. I am connecting every city to every other city, and then on there I'm going to be writing the amounts. So this is going to be something called a weighted graph because it has weights to it. Each edge has a specific value or weight attached to it. So S to A, San Francisco, Albuquerque, that's 150. So let's label that with 150. S to L, San Francisco, Los Angeles, 84. L to A, Los Angeles to Albuquerque, 125. So I could put it right here, I could put it right here, but it's the same edge, so it's going to be that value either way. San Francisco to Phoenix, that's 119. Los Angeles to Phoenix, 69. And Albuquerque to Phoenix is 84 again there. Okay. And so let's make one more note here. This is an example. This is going to define a couple of things for us within the context of this example rather than writing down a bunch of definitions without context. I think this is better most of the time. So this is an example of a traveling salesman problem. I didn't tell you that there's a salesman that's traveling, but that's the idea. So these traveling salesman problems, they've been famous problems for a long time, and people have thought about what's the most efficient way or the best way if you're going to make a trip to each city, something like that. What's the best way to do that, or the least expensive way? So that's what we're really focusing on here. What's the cheapest way to do something, or the most efficient way to do something? Here the graph is a weighted graph because each edge is assigned a specific value. I would pause the video to cough, but I'm afraid I would be pausing every other minute. So no, not going to do that. That's our first example. Hopefully I'll be able to make it through this lesson without passing out or something like that. I tried to take a little nap here earlier. But we're going to be coming back to this problem and actually figuring out what we were talking about, what the cheapest way is to go if you had to travel to each city. But for right now, just getting the basics down there and seeing what a weighted graph is and an example of a traveling salesman problem. Okay, let's move on. Pardon me, to a couple more definitions. A Hamilton path. I feel like we do really need to define what that is. That's what this whole lesson is centered on, Hamilton path and Hamilton circuits. So Hamilton path is a path that contains each vertex now. Before it was edges with Euler paths, but now it contains each vertex of a graph exactly once. In a Hamilton circuit, is a path. So remember, every circuit is still a path, but not every path is a circuit. Circuit has to begin and end at the same vertex. So that's what it is. It's a path that begins. I think, yeah, I want to write that. It's a Hamilton path. Is a Hamilton circuit is a Hamilton path, meaning that it contains each vertex exactly once. It's a Hamilton path. That begins and ends at the same vertex. Okay, and then a little recap about Euler paths and circuits and Hamilton paths now and Hamilton circuits. So you might ask, Mr. Wagner, I don't really understand the difference between these two things. I think you mentioned something, but I don't remember what you said. So let's put this in a different color. What's the difference? Let's put that off to the side. This is the difference right here. So as simply as I can state it, with Euler paths and circuits, each edge, that's the big thing, each edge must be included. This is exactly once, but each edge has to be included. And with Hamilton paths, each vertex must be included. So that's the big thing there. And then one more thing I want to define here, a complete graph is a graph that has an edge between each pair of its vertices. And then, for example, I'll draw a couple of examples down here, real quick ones. Okay, this would be a complete graph because there's a edge between each pair of vertices. This one has an edge between there and there. Notice it doesn't have two pairs. You don't need to have that. We're not looking for that. Here's one with 4 vertices. So if I did this, and this, ask yourself what's missing here in a second. So yeah, I've got a pair here to here and here to here, but this one also needs to be connected to this one, and this one also needs to be connected to this one. So now that's a complete graph. And if I had a pentagonal looking one, I connect all of those, and then I connect each point to each other point, and it looks kind of like a star there. Alright, so that one ends up looking like that. We could keep going with this, but let's just make a little note over here that each or every complete graph, I'm going to write note above this, so this is an important little note. Every complete graph has a Hamilton circuit. Not saying it has an Euler circuit, it has a Hamilton circuit. So we know that that's going to be true, meaning that I could start at any point here, and I could touch each vertex exactly once and return to where I started. I could touch each vertex exactly once. Boom, 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 boom. Notice I didn't include every edge there, but I did include every vertex. So that's the key part with Hamilton graphs or Hamilton paths and Hamilton circuits. From what's here, I could go from here to here to here to here to here. That would do it for me. I would leave out all those outside edges. I could also go around the outside, and that would be totally fine too. So every complete graph, though, has a Hamilton circuit. So let's check out a second example now. And we're going to draw that pentagonal one again, but we'll give it some labels this time. Give all the vertices some labels, that's what I mean by that. So connect each point with each other point. Edges need to be connecting all of those, and let's just go with A, B, C, D, and E. And we're going to try to determine a Hamilton circuit here. So this is a complete graph. And so there's a lot of different options actually. But why don't I label one here? And so if I started at, let's say I start at C, and I go in the direction towards D. So I'm going to put that, yeah, I think I can squeeze that in there. Okay, so let's do this in a different color. That'll be 1 right there from D. Then let's say I went to E, call that 2, and then from E I go to A, I'll call that 3. Notice I'm kind of making a funky little shape here, so this will go 4, and then back to C. I gotta go back to where I started and make that a 5. And so I'm going to start and end right here at C. This would be listed out as C, D, E, A, B, C. This is one possibility. Is it the only possibility? No, definitely not. But let's use a little highlighter here. So this is the way I went. So I went from C to D to E to A to B, and then back to C. So that's what I ended up with. You don't need to highlight, you can just put that there, but if you want to highlight it, that's fine by me. That helps you out there. So this is one possibility. Are there more? Absolutely. And I'm not going to have you draw more of them, but I want to point you to where they are. So, or where, not all of the examples, there's actually a lots of different ones, and we're going to talk about exactly how many there are in just a moment. But more are listed on page, I want you to write this down for me, on page 852 in example 2. The big question, can we answer this? How many total are there, though? So let's talk about that down here. So how many are there, though? We are going to answer that question in this box. So the number at the end, I promise, there we go, the number of unique and I'm capitalizing this because this is capitalized in your book. It's like a big deal to them. It's a pretty big deal, yeah. Number of unique Hamilton circuits in a complete graph. With n vertices. So up here we had 5 vertices. Complete graph with 5 vertices. It's always this, n minus 1 factorial. That's the big thing to know. So we talked about factorials in our probability chapter, and so we should remember what those talking about, or what those mean. So we have here to be 5 minus 1 factorial, so therefore I'm going to write down the answer to that question right here in example 2. There are 5 minus 1 factorial, which equals 4 factorial, which would be 24 possibilities. And so I was thinking about this more, and what it's saying here is, assuming you start at the same vertex, how many could you draw? At least that's what I was deciphering when I was trying to figure this out a little more closely. So we could start here. We can go in any one of 4 directions from C. We could go from A to B to D or to E. If I choose one, though, then I'm only going to have 3 more choices to choose from. So it would be 4 at the start, and then 3 from wherever I go next. Because I've already gone to C, I don't need to go back until the very end. So 4 and then 3. And if I went to B, I'd have A and E left, 2 choices. If I went to A, then I'd have just 1 choice left, and then I gotta go back to C. So that's kind of why that works out there. Why it's n minus 1 factorial. Excuse me. You might know that guy. You might recognize that guy. We're going to talk about him after example 3. So how many unique Hamilton circuits are there in a complete graph with, and this will be broken down into 4 different parts here. Okay, so let's say you have 3 vertices. B is going to be 8. C will go with 11. And then we're going to get crazy. We'll go with 50 vertices. And so with 3 vertices, it's just the n minus 1 factorial. I'm just using that idea. And so we have 3 minus 1 factorial, which is 2 factorial, which would be 2 times 1, which would be 2. With 8 vertices, 8 minus 1 factorial, that's 7 factorial. You put that into a calculator, you're going to get 5,040, or if you work that out, same thing. 11 vertices, 11 minus 1 factorial, which is 10 factorial, which you'll notice these things are getting bigger very quickly. So 3,628,800 is what 10 factorial is. And then 50 minus 1, 49 factorial, in other words, If you take a calculator out and work that one out, is there a factorial button on this calculator? If there's not, oh, there is. Okay, 49. If there wasn't, I wouldn't bother doing this one. And so this is a very large number. It's not just 6.08, it's 6.08. And then this is like scientific notation here. It's times 10 to the 62nd power. Whoa, that's a huge number. Okay, so this is a number with 65 digits. And so this is an approximation of what it is, 3.04. Oh, sorry, that's a different number. That is 6.08. Sorry, 6.08. 6.08 times 10 to the 62nd power there. So what I meant to say, that's a number with 63 digits, because we'd be moving that decimal 62 spots to the right. And so, so this is an approximation of that. As you can see, the more and more things you get, so this would be like the 50 states with an edge connecting each state. How many different ways are there to travel from one state to another state to another state, and make sure you hit all 50 states? If you could fly to these states and land like that rather than taking a road trip, there would be 6.8 times 10 to the 62nd power, an enormous amount of possibilities. Computers, even supercomputers, these values start to get so high that they can't even do this in a reasonable time. Like, it will take millions of years for a supercomputer to do certain calculations with the traveling salesman problems. So we have some different ways to attack that, since we can't wait millions of years to figure out the answer to a question when we're probably not going to be around in 100 years. Sorry to be morbid there, but just being a realist, we can't wait that long. Supercomputer's not going to last that long, neither are we. And so I wanted to talk about this guy, Kevin Bacon, a little bit here in the book. I would highly recommend reading what the book says about him there. But you may have heard of this idea with Kevin Bacon. You're trying to find a Bacon number, and so there's these guys that hypothesized that every single actor that has any sort of fame at all, I guess, so any famous actor can be linked to Kevin Bacon, a movie that Kevin Bacon's been in 6 connections or less. And so this is an application of graph theory. If you want to know more about that, though, I would highly encourage you to read more about this. Very intriguing, I think, but page 852, there's a lot more on that. So is it possible to find a connection between Kevin Bacon and each actor? So if he started a movie that somebody else was in, and then that person started a movie that somebody else was in, that would be a two-step connection, and so on. Pretty interesting. I find that intriguing, at least. Okay, so next up, though, let's talk about the traveling salesman problems. And what we're really trying to do here with these problems, I'm going to break this down into 3 different points here. Our goal is to find the least expensive, or sometimes we're looking for the shortest, way to travel between destinations. And a second point, the Hamilton circuit with the lowest cost or shortest distance, you might see that instead, or smallest value of whatever you're looking for. That is called optimal solution. So that's another definition, another vocabulary word, optimal solution. It's going to be the lowest cost or the shortest distance one, and a complete weighted graph. Okay, the book puts a comma in between those two things, so I'm doing that here too. The complete weighted graph. We already saw what a weighted graph was, and we saw what a complete graph was, so this is just a combination of those two things. It's a complete graph. With the weights. Or numbers. This could be the airfare amount, the distance amounts, etc. listed on the edges. And I'm going to say, as in example 1. So that's a big thing to remember with traveling salesman problems. And then we're going to talk about two different methods to solve these. Sometimes this method will work. If there's not too many vertices, the brute force method is actually what we call it. And it's just like it sounds. We're going to figure out everything. We're going to just use brute force to figure this out. So a brute force method of solving traveling salesman problems. Here's what we do. So to determine, we're trying to find the optimal solution. To determine the optimal solution, step 1, you're going to represent the numbers with a complete weighted graph. That's step 1. Step 2, brute force here. We're going to list all the possible Hamilton circuits. And so this gets very difficult to do, especially by hand in a hurry, because, okay, you start with 3, you've got 2 possibilities. That's not that hard, but you get up to 8 and you're already at 5,040 possibilities. You definitely would want to use a computer for that. And then if you get up to values like this, or especially like this, even a computer isn't going to do you much good in terms of the brute force method. It's going to take it a long time to figure out that. So we're going to talk about later what am I doing here and that one. Next slide there we go. Talk about another method to approximate solutions when the brute force method is just unreasonable. So got that. Step 3, determine the cost or distance, etc. You could say for each Hamilton circuit. And finally, step 4, find the Hamilton circuit with the lowest cost. So I think fairly intuitive, as long as you remember to find each possibility and then determine the cost for each one and pick the cheapest one. You've got what you need to do. So let's go back now to example 1. We're going to use the information in there, and the information I found in example 1, this is the first time I'm looking at this, so hopefully I won't make any mistakes here. As always, check for mistakes in my videos. If you see anything, write down the time you saw it, what the thing was. Help me make these videos better, and you might get some extra credit if you're one of my students. So we're going to use the brute force method and the table slash graph from example 1. To determine the optimal solution to visit each city, starting and ending, since I'm closest to Los Angeles right now, where I live, I'm just going to say we're going to start and end in Los Angeles. So starting and ending the trip in Los Angeles. Okay, and so off to the side here, I'll redraw the graph just to make it a little easier for us. And I think it's kind of funny that it spells slap or pals. Anything else you can think of? Laps. But each one there was, we're just recreating this, so 150, 119, 125, and 69. 150, 119, 125, that's a 9, and 69, and I believe this was 84 and 84, both parts there. So let me just double check that quick. Too far. 15, 119, 150, 119. Okay, looks good to me there. Alright, so we've got all our edges labeled, and let's make a table. Now we're going to be using, since there's 4 vertices, and we're drawing a complete graph here, we have a complete graph. How many possible Hamilton circuits are there? If we start at Los Angeles, we've got 3 choices first, and then 2 from there, and then just 1 from there. So it's that 4 minus 1 factorial idea. In other words, 3 factorial, which is going to be 6. After 4, there's a lot to figure out. After 4, you'd have 5, which would be 4 factorial, which would end up being 24. You'd have to do this 24 different times. Don't worry about having to do this more than 6 times. I'm not going to make you do something like that. You would hopefully have the use of a computer for anything more than 4 vertices or something like this. Okay, but we'll need 7 total blue lines on your paper here. I'm going to make this my Hamilton circuit, listing out the circuit, and then we're going to have 4 different legs. So this will be my first leg, my second leg, my third leg, and my fourth leg, and then finally here will be the total cost. Okay, and so I'm going to make yellow lines again. These will be your blue lines, so I don't feel the need to draw in these lines. 3, 4, 5, and 6 will be this last one down here. Alrighty, so here we've got a Hamilton circuit, is what will be listed there. This will be the first leg along with the cost. This will be the second leg and the cost of that. This will be the third leg and the cost of that. Fourth leg, cost of that. And finally, the total cost over here, what I care about the most. Okay, so let's list them out. You should have 6 possibilities. And where that came from again was, why are there 6? It's just 4 minus 1 factorial, which equals 3 factorial. That's why there are 6 possibilities here. So let's list them all out. I could start at L and go to S, then go to A, then P, and back to L. So that's one possibility. So L, S, A, P, and back to L. Another possibility, I could start at L and go to S, and go to P next, and then to A. So San Francisco, Phoenix, Albuquerque, Los Angeles. Another possibility, I'm starting at L for Los Angeles each time. But I could go, instead of San Francisco, I could go to Phoenix, and then to Albuquerque, San Francisco, or I could do Phoenix, San Francisco, and then Albuquerque, or I could do Albuquerque, and then Phoenix, San Francisco, back to LA, and finally Albuquerque, San Francisco, and then Phoenix, and back to LA. So these are my 6 possibilities. And so let's figure out what the cost would be for each one of those possibilities here. So I'm going to use my calculator to do this, and I'm just going to follow along on the graph that I've made here and add them up. So LA to San Francisco looks like it would be 84, and then to Albuquerque, so San Francisco now to Albuquerque, that's 150 right there, plus 150. Then to Phoenix would be another 84, and then finally back to LA from Phoenix would be 69. And so that would give me 387. And so that first leg cost would be $387. My bad, I just figured out the total cost there. So this is the total cost. It's going to be $387. But this is LA to San Francisco. We said that was 84. This was San Francisco, then to Albuquerque. That was the 150. And Albuquerque to Phoenix, that was 84. And finally Phoenix back to LA, 69. Okay. And so we're just going to do the same thing with the rest of these. Looks like this will stay the same. And you can see that this is a little tedious, but it's not difficult. Definitely not difficult to do these things, not hard to figure these numbers out. You just have to take the time to do it. So let's see, we got L to S, S to P would be 119, P to A, 84, oops, P to A, and then finally A back to L, looks like 125. So let's see if that was any cheaper. 84 plus 119 plus 84 plus 125. Nope. So that looks like definitely not the way we want to go. Let's check out the rest of these. We got L to P, and P to A to S, and S to L. So Los Angeles to Phoenix, 69. Phoenix to Albuquerque, 84. Albuquerque to San Francisco, 150. And back to LA, 84. So let's see what that gives us. What am I doing? There we go. Pressing the. I'm trying to use my finger on this tablet thing. That's not what I'm doing. Gotta use the pen on that. 69, 84, 150, 84, 387. Okay, so we got one that costs exactly the same as one of our previous ones. Now let's check this route out. So get this. That one, and why don't I just fill in the rest of these like that here. So L to A to P, P to S, S to L. Finally here, got that. So L to P, 69, P to S, 119, S to A, 150, and A to L, 125. I see that one's not looking too good to me. Seems like that one might be the most of what we've done so far. But let's figure this out. So 69 plus 119 plus 150 plus 125, 463. Yep. So definitely don't want to go that way. That's to Albuquerque, then to Phoenix, then to San Francisco, and finally back to LA. Let's see what we have here. 125 plus 84 plus 119 plus 84 again. There's another 412. And finally L to A, it's the same thing. Albuquerque to San Francisco. 50. San Francisco to Phoenix, 119. Phoenix back to LA, 69. Okay, let's see. Whoa. Let's see what that gives us. I didn't lift my pen there. Not sure why that happened. 125. Not minus, plus. There we go. 150 plus 119 plus 69, and I didn't do that right. Let me see. Something is off there. 125, 150. That's where I made a mistake. 119. Okay, 463. So happened to work out that these two are both the same, these two are both the same, and these two are both the same. The example in your book, similar to this one, that also happened. So I would hypothesize, I would theorize that might always happen, that you're always going to have two matching up with each other if you have something like this, but can't say I can prove that's true. I'm not sure. That'd be an interesting thing to look into. So these two, though, are the cheapest ways to go, so you could pick either this way or this way. I think it's because one is just the, yeah, that's why it is. So the book does talk about this. So one is just the reverse of the other. So I'm going to, in a highlighter, you don't have to do this part here, but just to see what we got here. This is L to S, and then S to A to P, and P to L. So we went this way around. But if you went the other way around, it'd be L to P, then to A, then to S, then to L. So it would include all the same edges. That's why it's going to show up twice like that. Oh. Yay! So based on the results above, and since I've numbered my options, I can say options 1 and 3. Options 1 and 3 would be the optimal solution. Or in other words, i.e., that is to say, least expensive. So if I were a salesman, I was trying to travel to these cities and get back to where I started from, I would definitely want to take either that route, or I could go this direction. I could take the route going this way as well. So as long as I start and end Los Angeles, again, you don't have to draw the highlighter stuff on the pictures. That might just make it more confusing to understand, but looking at it later. But just know I'd go in either that direction around or this direction around, come back to LA. That's going to be the cheapest way to go, rather than crisscrossing like that or anything of that nature. Okay. We're still going on this one. There's a lot in this lesson. Probably going to be one of our longer ones for this chapter. Let's check this out now. So here's a little note to make. We've mentioned this already. I've mentioned this already. When the number of vertices n increases, n minus 1 factorial increases very rapidly. Quickly becoming impractical for even supercomputers. Really powerful computers. It's even impractical for them, supercomputers, to calculate. So, dilemma. That's saying even the supercomputers, you get the vertices too big, they use the brute force method and it takes them forever, longer than our lifespans, to figure out the answer to one problem. So since that is the case, we don't have any theorems that have been proven to help us find things out any faster than the brute force method. I don't even know if there's a possibility that a theorem could be proved. You might have had somebody out there that proved that it was impossible to prove that. Sometimes they do that. They say, oh, it's not possible to prove it. Somebody proves that something is impossible to prove. So because of that, though, this is a way to find an approximate solution. And so this won't always give you the cheapest one, but it will give you a pretty good value, a pretty good approximate solution, in other words. So the nearest neighbor method. And here's how we do the nearest neighbor method. It's kind of like it sounds, just like the brute force method. You just kind of keep going through things with brute force. Nearest neighbor, which one is nearest to the next one? Or which one is the least cost from one to the next, and we just keep using that. So to approximate the optimal solution, we're going to go through these steps. Step 1 is to represent problem with a complete weighted graph. Step 2, you need to identify the starting vertex. Step 3 is to choose the least expensive or shortest edge from there. Step 4, you're going to be at the second vertex then. So at the second vertex, choose the least expensive or shortest again. Just depends on the type of problem you're doing. Least expensive or shortest edge leading, there we go, leading to a vertex not yet traveled to. So we don't want to go back from where we came from. We would be not creating a Hamilton circuit. Then we have to travel to each vertex exactly once. Not yet traveled to, there we go. And then step 5, you're going to continue that idea, so continue the process until all vertices are visited. And finally, step 6, travel back to the original vertex. So we are going to use that nearest neighbor method to do example 5. And this will be it. I promise this will be it. Okay, so we're going to now use the nearest neighbor method to determine an approximate solution. So this might not be the best one, but because it's just impractical to figure it out, otherwise we'd be having to figure out a lot of different possibilities. So approximate solution, if we get past 4 vertices, we're going to be using this method instead when we're doing things by hand, excuse me. For the complete weighted graph below. And we're going to start and end, starting and ending at vertex F. Okay, so let's make we're going to make a pentagonal one again. So a complete graph, every vertex needs to be connected to every other vertex with an edge. There we go, and hey, may the force be with you on this one. Why do I say that? Oh, there it is. Okay, so we're spelling out force on this one. So let's determine what we got here. I need to label some things though. So this is a complete graph, but it's not yet a weighted graph. I don't have the weights on here. So say that's 15, 44 down here. I think I'm going to make this a little bit bigger. Yours can stay the same size though, don't worry about it. Come on. Let's see if that's okay. That's a little bit bigger. I didn't want to select the whole thing, but it did not want me to select the whole thing. It appears this is 132. It's a 3 right there. I'm going to say this one is 107 from C to R. O to C. It's 250. That's an expensive one. 230 from O to E. 230 from O to E. 210 from O to R. From F to C will be 14. From F to E will be 17. And let's see, does that do it? I've got all 4 connected there. 1, 2, 3. Excuse me, I've got a value for. Yep, I got a value for each one there. Okay, so let's solve this bad boy. Let's solve this puppy here. We got the nearest neighbor method. Gives the Hamilton circuit. And let's see what it is. So I'm going to get out my different color at this point and go over things. So I'm starting at F here. I have to start and end at vertex F. So right here is my starting point. And I'm going to be going from here, and I'm going to find the cheapest one or the smallest one. So the smallest one I see here is this way, 13. So I'm in my different color. I'll put a 1 next to that. And so I'm going to connect that one to that one. So now I'm here. And then from there, I can't go back the way I came from because that's not going to make a Hamilton circuit, so I need to go back. I need to choose another one of the three vertices I haven't visited yet. And I'm going to pick the one with the smallest value. So 210 of those is the smallest value. This is going to be a 2. Let's trace over that now. Going in that direction. Now we're at R, and then can't go back to F, can't go to R yet, or to O, can't go back to O. I need to pick C or E. Of those two, E is the smallest value, or that edge connecting those two is the smallest. And now that I've visited F, O, R, and E, I have to go to C. That one I haven't visited yet, so I have to go in that direction. And now I've visited every vertex, and so I need to go back in that direction here. So that would be I think I spoke myself there. That should have been a 3 right here, a 4 right here, and a 5 right here. So you can kind of see why I wanted to make the picture a little bigger. I just don't want to jam pack too much stuff in there. So we went 1 to 2 to 3 to 4 to 5 back to where we started. And so what that looks like listed out is F to O to R to E to C, and then back to F. So that would be, according to the nearest neighbor method, an approximate solution. Is it the best one necessarily? No. You might be able to find a cheaper way, or a shorter way, or a smaller value way. But again, after a while, it becomes very impractical, sometimes impossible, to figure out what the exact solution is going to be, or what the best possible optimal solution is. So sometimes we have to refer to this. So the approximate solution, the sum of the edges associated with the circuit is, we would have, looks like from, I'm going to use my different color on this one, so I would need to know from F to O. I'll put that right there, and then from O to R, from R to E, from E to C, and finally back from C to F. And so from F to O, that one was a 13. I'm going to add that with O to R was 210. R to E is 44. C to E 132. And then C to F was 14. So if we add all that together, let's see what we get. 13 plus 210 plus 44 plus 132 plus 14, 413 it is. So I didn't say this was dollars, I didn't say this was miles, I didn't give these units, so the lowest value is just 413. And I want to make one final note that goes along with the problem we just did here to say this. So the approximate solution may not be the cheapest or shortest or smallest, kind of depends on the context of the problem as to which one of those words you would pick. But sometimes we are forced to use it because B/C for because, using the brute force method would be impractical. So we talked about that already, how supercomputers, even if you get to a certain point of vertices, number of vertices, even they take way too long to figure out the answer to these problems. But one final sentence here, it may, or it generally will, provide a value lower than most possibilities, however. If you want to read a little bit more about that, I would say, however, there we go. I would say you should look at the final paragraph in the book, the textbook, on page 856. So they talk a little bit more about this and why that is, or why we use approximate solution on that whole that whole page there. Actually, example 6 in the book. There's 6 more examples in the book. Don't forget about that Kevin Bacon thing. I think that's totally worth reading on there, and hopefully that will be helpful. Also, if you have time, read the profile and mathematics part on page 850 about this guy here. Got a lot of slides in this one, not Bacon. This guy is William Rowan Hamilton. This is who these things are named after. So some pretty fascinating stuff. Apparently he was on a walk in the park with his wife. He got really excited because he figured out the answer to the problem and etched it on the bridge, as a stone on the bridge. He was passing by, and it's still there. Discovery he made about quaternions in abstract algebra. Very exciting stuff. Okay, I'm done. I'm going to probably go to sleep now and hopefully feel better. But I hope you are feeling well, and hope this helped you out.